is one case. Okay, so-called embedded point, and v sub a equals 0, then basically it goes like this. Okay, now I'm talking about the situation. Now, point A on the rigid body always was fixed, all right? It always was fixed. It was B that was not. It was B that was the bug, that was, had the luxury of moving around. And now, here we go. Okay, that's half a bug, and it's fixed. The point is, it cannot move. It's on the object. So, yes, ma'am. This here?
The one below.
Oh, yeah. When I finished the, I was going to say this A here, V sub A, is that A. All right. The thing is pinned down. It's not going anywhere. What I was about to say is that the point of any other point, P, any other point P on the object's velocity as seen from the ground is given by simply this, omega cross r, all right? Where RAP is from the point of rotation to that. And what that is you can appreciate, that's simply a special case of this, all right? When point B does not move, when point B or P for that matter, is embedded in the rigid body, this by definition goes away. All righty? So all there is omega cross r, and that's it. All right. So let me simply say we're going to introduce the concept of. I'm sorry.
Would that just be VP?
This B? Yeah. I'm sorry. This is. Yes, it is. I'm sorry about that. Well, it doesn't matter. In this case, it's the same. Because A is 0. But good enough. Okay, this is A, and A is fixed. All right, and P is somewhere else. I shouldn't have introduced P. Needless. All right, makes sense? And if this is omega, then yeah, let me actually draw my figure here. This is called instantaneous centers. All right, now imagine we're back to our old friend, the wheel. This is an example. Rolling without slip or non-slip rolling. Okay, so here we are. We got a wheel of radius r, center C, point of contact with the ground A. The whole thing is rotating with an angular velocity omega. Okay, so the situation is this. What can you tell me about this point right here? What about the lady in the front row? Yes, ma'am. Yeah, you're Laura. Okay, what can you tell me about point A? Excuse me, point A's velocity.
It's at 0.
It is 0, absolutely. By the way, were you talking about point A on the ground or point A on the wheel? They are the same thing, exactly. But the one that's relevant for our discussion, because V sub A on the ground is always 0. As far as the wheel's concerned, it's 0 only at this instant. Makes sense? An instant later, and it's going to be somewhere else. So this little guy right here is called the instantaneous center of rotation. Why do we care? Because this is a very nifty little item, because what it means is that, back to Ronald and, I'm sorry, what was your, it was Danny? Or what was your name?
Darren.
Darren, sorry. I thought it was your question, is that the relevant point is that if this point on the wheel has 0 velocity, if this point on the wheel at this instant happens to have 0 velocity, then conceptually at this instant, the entire wheel, the entire rigid body can be thought of as rotating about that point. Make sense? So, here's an easy one. How about, is it Laura or Lauren? I couldn't remember. Laura? Yeah. What would you guess the velocity? And so what I'm asserting is that this durable little formula right here okay, is gonna work for us. Now, first off, when I say omega here, if that's what the omega vector, can you appreciate that's a scalar that's actually pointing off in the negative k direction? Okay, everybody got with me here? This is a vector. When it has a scalar value omega. Okay, but it is a vector that's minus k. So because k is going, k is out this way, but the omega right-hand rule is that the vector in question is pointing into the board. Everybody with me? Okay, so Laura, point C happens to be the center. Where's it moving? What's its velocity with respect to the ground right now? And how will you find it?
You just use the omega cross r.
Yeah. What's the what is the r of which you speak? Right there.
The r like between A and C.
Yeah, from A to C. Okay, that's exactly right. So if you want to get really pedantic about it, you would do this. All right? Everybody with me? Okay, you're absolutely right. That was an easy, and I'm sure you know it goes out, it looks like this. It happens to be, in this instance, perpendicular to R sub AC. Goes off in that direction, has a magnitude R times omega. That would come straight out of that. How about the lady right behind you, next to Marion? Your name again? Oh, Payal?
Yeah.
Payal. She got an easy one. How about, here's one. Let me just pick one. Let me call this P1. That point over there, okay?
So,
Kind of same altitude as C, but bringing up the rear.
so I would use the omega cross r again.
Okay.
And
I know what omega is. What's R?
it's the vector from A to P1.
That's exactly right. Very good. It's like this. Okay? You got it? So you put that into, anyway, this thing's got, this is a vector, excuse me, this is a vector. It's got a horizontal and vertical component, I, J, all that. This is a vector quantity, okay? You do the math, and what comes out the other side? This is going to look like.
It's gonna be.
Do cross products in your head? It's actually easier than it seems. Now let me just say, this is where there's definitely two kinds of people, okay? when you ask this question, there's one that goes, oh, geez, hang on a second. R sub A P1 is some I and such a J. All right, and omega is this J. And anyway, you write it all down. You're really tracking the math of it, okay? There's another school of thought that basically says, you know, the geometry of the situation tells you a great deal. Where is the vector omega pointing? Yeah, into the board, right? Where is the vector r pointing? That way. Okay, so what happens when, and those are by definition perpendicular, no? Yeah, because they just are. And a cross product, what do you get when you do a cross product of A cross B? If they're perpendicular, you get the full magnitude of both multiplied together, and it's perpendicular to the two of them. Okay, so omega cross r is this way.
Oh, okay. Right, because it's into the board and then you follow the vector.
Precisely. Okay? Omega is in there, and that r is this way, so that vector cross this vector gives you one that's perpendicular to both. Okay? So it points out in this direction. You know its magnitude is this length times that number. Okay? Very good. Enough of that. And the great thing to me about the concept of an instantaneous center is that literally you pick the point, and within a very short time you can generate, you know what its velocity is. Now let me hasten the point. Okay, so that's an easy one. Let's do, yeah. I think we got time for this. Let me just check. Okay, that, yes. All right, let's do this. Here we go. Okay, let's do this. Let's say you got an internal combustion engine. Here's the connecting rod, or excuse me, the crankshaft, connecting rod. There's the piston. We'll say this is at 45. Okay, let me label these points. This one's O, this one's A, this one is B. All righty, everybody see that? Now let me just define the length of link 1. I'm going to call that link 1. I'm going to call this link 2. Notice these are scalars. These are not vectors. This is the length of the thing, and this is the distance, the scalar distance between the pivot, and this is fixed like this, and this whole thing is spinning like that. Now, it is a vector, but if you'll bear with me, this one is sufficiently simple. I don't think it really warrants treatment by vectors, but okay, so here's the deal. Given okay. Okay, this is link number 2. I want to know what, I want to know how that link is rotating. Okay, and I'd like to know what the linear velocity of that is. Okay, now I can appreciate that at first blush you might look at this and say, oh my God, isn't there someplace else I ought to be right now? But let me simply say, you stop and think about this just a little bit. Okay, here is point O, and this is point B. And this is point A. So here goes the reasoning. Now just watch this. This is the solution. And in the interest of time, I'm just going to knock this out here. If you would, just copy it down and think about it later, because I do want to get to this next section. Okay, so here it goes. Here's the way I would solve this problem. I know this length. This is R1. I know this angular velocity. And so I know this velocity. I know this distance. Because it's 45 degrees, see this angle, or see that line right up there? Now, what is this line right here? What this is, that the intersection of that line and this line says that this is the instantaneous center of rotation for the bar in question. Okay? And so here goes the reasoning. The instantaneous center of rotation is perpendicular to V1 and V sub B, because you know V sub B is in this direction someplace. Actually, let me give you a clue here. Excuse me, let me do this. Send both of these away. I'll give you the high level. This is the kind of high level answer to the question that was asked earlier. Basically, if ever you have 2 points on the object whose linear velocity is known, their perpendiculars define the instantaneous center of rotation. All right? So this is a rigid body, obviously. I'm sorry I have to cover that up momentarily, but here's where I'm putting the answer. Okay, so what this says is this tells you that the center of rotation is located at this is R3, so is this distance right here, because this is 45 degrees. That's where the ICR is. You know that velocity number one, V1, is simply omega 1 times R1. That's this. Excuse me, I call this V. Let me call this V sub 1. It's also VA. Then you know that omega 2 is simply V1 over R3 minus R1. Because this distance right here must be, no, I'm sorry, I've got a mistake here. Yeah, I have a mistake here. This distance is R4 minus R1, where R4 is the square root of 2 here. And the last one then is simply B sub B is equal to omega 2 times R3. So let me just give you the big picture here. The situation is that you know that the linear velocity of this point is perpendicular to link number 1. You know that this point is also part of this. You know that this is where the instantaneous center of rotation is located, because you know V sub B is over here in this direction, and you know V sub 1 is in that direction. Okay? So you can find the angular velocity of omega 2 by dividing this by this. All righty? That's what gives you angular velocity of omega 2, and that allows you to find the velocity of point B. Make sense? All righty? So the concept of instantaneous centers isn't a, what do you call it, cure-all for everything, but it is a very useful item. And this is the end of segment number 3. Questions, comments before we go further? Yeah, your name, sir? Noah. Noah?
Yeah. How did you know that that point was the instantaneous center of rotation?
Excellent question. This kind of goes back to Devin's point earlier. The situation is that, you remember up here, it's by interpreting this. Okay, basically we're saying if there's some point that you know has no velocity, is zero velocity, then the velocity of any other point on the, like the wheel example here, when we know that this point was of zero velocity, and you know that conceptually the entire rigid body is rotating about that center, you know that the velocity of any point you choose is simply going to be given by the cross product of omega cross r, right? And it's going to be perpendicular, because omega is by definition perpendicular to the plane, so any vector in this plane is going to be perpendicular to.
How did you actually find that it was there?
Well, look at this. So if I would kind of imagine this weren't drawn, if all I told you was I got a rigid body here, it's got 2 points on it, and each point's velocity is known to me. I know what the linear velocity of point 1 and point 2 are. What you could say is, I know that that center, at instantaneous center of zero velocity, has got to lie somewhere along a perpendicular to this. And ditto, it's got to lie on a perpendicular to this. Therefore, the intersection got to be it, right? And so this is conceptually what's going on, is that that point and that point alone on this rigid body, right at that instant, there's only one point on that object that has zero velocity. And that's it, right there. Just like this wheel over here. There's only one point on that wheel that has zero velocity right now, point A. Okay, does that make sense? Any other questions on that? Yes, ma'am, in the blue. Name?
Christine.
Christine.
I was wondering, for the expression in V1, are we referring to only the velocity at point A, or as a point at R1?
This one here?
Yeah.
Again, because of kind of some sloppy notation on this point, on this issue, what I'm speaking of is the velocity of this point. I called it, one time I called it V sub A, and another time I called it V sub 1. It's the same concept. Yes, ma'am. Your name?
Kate,
Kate.
on your original drawing, what does it say theta equals to?
Question is, what is theta here? Answer 45 degrees. Yeah, it was a trick, a clever trick on my part to avoid arithmetic. Okay, because as you know, 45 degrees, that makes this length the same as that one, and I don't have to deal with trig functions. The gentleman in the back in red, your name please.
Larry,
Larry.
why did you change the R3 minus R1 to R4? What is R4?
Oh, yeah, I'm sorry, that was a mistake on my part, to be honest. If I may, just for clarification. Does that make sense? Because it's the hypotenuse of this isosceles triangle. And the relevant part that I wanted was this, the length of this segment right here, which is the difference between those two. Make sense? Okay. Anyway, that's it. That's what it's all about. Nico.
Omega 2, physically, what's that describing?
You see this crank, this connecting rod that's going like, is this thing goes around like this? I'm sorry? I understand what the system's doing. Oh, good. Well, what I was going to say is you're the one who told me that this connecting, whereas this is going through pure rotation, this one's going through pure translation, this one's doing both. So it is both translating, which we don't care about, but it's also rotating, which we do. And that's the question. Omega 2 is the angular velocity of the connecting rod. That's the question that's what this question is asking. At this instant, how is the connecting rod rotating? Or more exactly, what is the angular velocity of the connecting rod? Make sense? Okay.